Please, OVIDIU.
Thanks for inviting. It's my pleasure to talk about exploring Brownian motion on diverse structures today. So let me tell you a little bit about myself. I start being a differential geometer back in the day, in 90s. And the way I learned differential geometry at the time was just using geometry, linear algebra, and some basic calculus like everybody else, following Kobayashi and Omizu's textbooks. But meantime, in order to survive, differential geometry has to readapt and reinvent itself in a number of ways. So I have here a little table saying that differential geometry plus partial differential equations and ordinary differential equations led to something called geometric analysis, which is one of my main field of study in the last 25 years. Also, differential geometry can cope with probability and statistics, and that leads to another branch of differential geometry today called information geometry. I also authored a book in this kind of field, information geometry right here. Also, differential geometry can be mixed with stochastic calculus, which leads to stochastic differential geometry, which is going to be the subject of today's talk. And I also have a textbook in that actually appeared 2 years ago. And also differential geometry in a very latest stages can be mixed with deep learning and machine learning, which leads to what is called geometric deep learning and geometric machine learning, which is probably the latest applications of differential geometry. So today I'm going to talk about how differential geometry and stochastic calculus can come together and what kind of new results we can get out of this. So the main ingredient when we talk about stochastic differential geometry is to think of some stochastic objects which can be studied on a manifold, Brownian manifold or any other kind of manifold. Now, like in the regular differential geometry, we study vector fields, we study the metric tensor, we study these kind of things, curvatures. But when we do stochastic differential differential geometry, the main object is to study diffusions. So diffusions which spread along the differential manifold in a certain manner and being influenced by the geometry of the manifold. So to understand what I'm going to talk about in the next slides, I want to give the definition of the one-dimensional Brownian motion, just in case some people are not in that field. So a one-dimensional Brownian motion is a stochastic process. So you can think it as something like that. So whenever you simulate this stochastic process, you get a completely different path. And all the paths are completely different. The only thing which remains the same is the fact that the increments or the jumps between different time instances, they are all the time independent. So independent increments and also normally distributed increments. So the difference between those two values of the Brownian motion are normally distributed with a mean 0 and variance t minus s. So that's a one-dimensional Brownian motion, which is actually the building block of the entire theory. So once you have a Brownian motion defined in one-dimensional case, you can also define a Brownian motion in the plane, or a two-dimensional Brownian motion. And the two-dimensional Brownian motion represents a stochastic process, a two-dimensional stochastic process, for which each component is a one-dimensional Brownian motion, and those two components, the x and the y, are independent. Now, a very interesting situation about this, similarly you can define an n-dimensional Brownian motion on an n-dimensional Euclidean space. Now, I've seen that many people today applied their talks to different botanical applications or other kind of applications. Here there is an interesting application of application to the way life spreads in the universe. So the way I see that life spread on Earth is as a Brownian motion. If you think the Earth is modeled by a two-dimensional manifold, and the seeds and the viruses and the bacteria, are spread along the Earth according to a Brownian motion, which probably is in a certain extent true, because if you have more than a certain number of, let's say, more than 30 error terms or error influences on the trajectory of a particle, then you can consider that being a Brownian motion. So we notice that on Earth we have life on every single little island, remote island, or any, the mountains, peak of the mountains and things like that. So because the life spreads as a Brownian motion. So this is related to a property of the two-dimensional Brownian motions, which is called a recurrent property. So the Brownian motion is recursive. In other words, if you look at one of those squares here, so one of these squares represents a domain, a compact domain in the plane, and the probability that the two-dimensional Brownian motion starting at the origin to reach that little square is equal to 1, regardless of that square. So this is called the recursive property of the Brownian motion, which says it visits with probability 1 every single location in the plane. So that's why life, when it spread it on Earth, it reached in 5 billion years with probability 1 every single island. Now, something interesting happens that in spaces with more than 2 dimensions, for instance, in the 3-dimensional space, the probability that the Brownian motion will reach a certain region is not equal to 1. It's always less than 1, case in which we say a 3-dimensional Brownian motion is transitive. So this probability is inverse proportional to the distance from the origin to that region. So that's how we explain that in space, in the 3-dimensional space, if you think that life spreads in the universe according to a 3-dimensional Brownian motion through asteroids and meteorites and comets and things like that, life didn't spread that much. So in all planets we've been to so far, we haven't seen any sorts of life yet. It's because the life doesn't spread with high probability when the dimension increases. So this is on the side. So once we know what a 2-dimensional Brownian motion is, I'm gonna talk about a new object. It's an object people have studied for thousands of years, but our point of view today, the novelty of our point of view is the fact that this triangle ABC is considered with the vertices A, B, and C non-deterministic. So when you study a triangle or a polygon in geometry, you think that the vertices are fixed. They are deterministic and fixed. And you study different sorts of properties, for instance, the perimeter, a formula for the area, and other kind of properties. So in today's talk, I'm going to consider some triangle, ABC, and I'm going to call it the Brownian triangle because I assume that the vertices themselves represent Brownian motions in the plane. So why do I study something like this? Because in nature, nothing is fixed. If you think that these vertices A, B, and C are 3 points in the plane, or 3 points, let's say the plane, even the points in the plane on a piece of paper, they oscillate in a certain way at the microscopic level. If you think there are 3 molecules of water, so in the molecules of water do not stay fixed, they moved according to a Brownian law in the liquid. So it's worth studying this kind of new object. So the first thing I'm interested when I study a triangle is the area and the perimeter of such a object. So what I've done is this is the link where we can access the code. I've done a little Python code to study the area of such a triangle. So all the vertices of the triangle start at the origin and then starts diffusing in the plane. And that's how this new process, this is a stochastic process which models the area. When I talk about area, I talk about the absolute value of the area. It's something positive, starts at 0 and moves. You see, sometimes it might go up, sometimes it's close to 0 again, so it looks like there is no law. Actually, for a human eye, or for our visual cortex, which is somewhere in our occipital, we cannot see any law just looking at simulations. That's how humans are formed. But if you I wrote another piece of code, I considered several simulations, and I made a histogram just to see what the probability density law is for the area. So I noticed that the probability density law decreases, maybe exponential, and for instance, after 10 seconds, this is the time here on the horizontal axis, and after 10 seconds, you see this probability law becomes very small. So there is a large spike near zero, and still, this is all software, so I didn't prove yet anything, but I'm gonna do that later. The next part is that I plotted, see, this is the law, and then I considered the expectation of the area. So what does it mean, expectation? To compute the expectation, I consider several times, probably 20 times, 20 instances of time, equidistant in time, and I considered many simulations, let's say 100 or 1,000 simulations for each instance of time, and I made an average of the areas obtained. This is called the Monte Carlo simulation. And I noticed something very interesting, that the expectation of the area provide us some values which are collinear. So this line actually, if you extend it, it passes through the origin. So the ansatz here is that the expectation of the area of a Brownian triangle must be a linear function of an unknown slope for the time being. So all those things have been realized using computer code. Now, where is the math? So here is the math. So I proved that, so first of all, we denote 1/sinh by cosinh, which is 2 over the difference of these two exponentials. And I proved that the probability density for the area process is given by this law. A very simple law. It's a product between x over t squared and cosinh of pi x over 2t, where x is larger than 0 because the area, as I said, is considered to be positive all the time. So we do have a law for the area of a Brownian triangle given by this interesting formula. Now I took this formula and I draw a few profiles for this probability law. These profiles depend on the value of t. For values of t small, we have the red one. For values of t medium, we have the green shape, and for t large, we have the dark profile. Now going back to our initial simulation here, we notice that our initial probability density function matches the red profile. Okay, then once you have the probability law, you can compute quite a few things. You can compute the moments, you can compute the expectation, variance, and so forth. So the first thing is to compute the p moment. So the p moment of a random variable represents the expectation of the pth power of that random variable. And in our case, we can compute explicitly that expression by hand, and it's given by whatever you see here on the right side, where this is a constant, p plus 1 factorial, pi to p plus 2, all those are constants. Psi represents the zeta function, the Riemann zeta function, the well-known Riemann zeta function, evaluated at p plus 2. And the only thing here which is a variable, it's the variable t, and appears as a monomial at power p. So roughly speaking, the pth moment is proportional to the monomial t to the p. So in particular, if you choose p equal to 1 and p equal to 2, we obtain the expectation of the area to be linear in time. It's 28t over pi cube zeta function of 3. So be linear, it means that it matches whatever ansatz we formed when the Python script showed us that those points are collinear. And now we have the mathematical formula here. And we can also compute the second moment, which is actually a quadratic function in t. And you can also form the variance of this random variable, which is a quadratic polynomial in t as well. So I'm not going to go through the entire proof. It's a relatively interesting proof. I have it in one of the chapters of my book. It's right here. I'm going to show you some tools I used to have a flavor of what kind of tools stochastic calculus uses, and those tools are completely different than what we have seen in usual calculus. So the area has been modeled as a determinant of the coordinates, like in analytic geometry, and then it has been written as an integral. These are all called Ito integrals, and they form what is called a martingale. It's a very specific stochastic process with certain properties. This kind of martingales are shown according to Dambis-Schwarz theorem that they are actually Brownian motions at the different clock. So we understand what the diffusion means. But if you change the clock of the diffusion, let's say the diffusion itself has an intrinsic clock, so a way of measuring time. But if you change the way you measure the intrinsic time, that process from an exterior observer doesn't look like a diffusion anymore. It's still a diffusion from the diffusion point of view, but from an exterior observer might be a completely different process. So in our case, this area is a diffusion eta according to this integral clock. This is an increasing function, which is actually a Wiener integral of a Bessel process. So this four-dimensional Bessel process represents a stochastic process which represents the distance between the origin and a Brownian motion in R4. So this is one ingredient in the proof, and another one is the Cameron-Martin's formula. So Cameron-Martin's formula, actually in its whole generality, it's written in this formula, and it's important because you can have a closed form expression for the expectation of the exponential of an integral of the square of a Brownian motion starting at x. So applying that, we have whatever you see here. This expectation of this function is called the characteristic function of the area sigma t, and it can be computed closed form as 1 over cosh squared. Another ingredient in the proof is called Levy's area. It's something which if you think of a Brownian motion in the plane, then the vectorial radius of that Brownian motion spans a certain area, and that area is given by this formula. So a similar formula exists in calculus. If you replace W1 by x1 and W2 by x2, you get the area in the plane, which is swapped by the vectorial radius. Sometimes it's called stochastic area of Levy, and it has a straightforward closed form formula for the characteristic function conditioned or pinned down at time t to be x. So all those are the ingredients which brought me to this formula, the formula I showed you before. Now in mathematics, whenever we get a formula, it's very nice if that formula appears also in other branches of mathematics, because in that way you can have a connection between different objects. And this is the case here, that this formula appears also in other branches. So I'm going to talk about that shortly. The probability density of the area is given by this law, and this law is supported for x non-negative. But if you consider the the area is the absolute value of signed area. Sigma t is the signed area, the area with the sign. So the signed area has a probability density on the entire real line. So instead of non-negative x's, we have all real x's. The only difference that you have to divide here by a 2. So you have to put a 2 here in front, because absolute value of x is an even function. And now, as I said before, this law appears also somewhere else. So where does it appear? It appears in an inner product of two independent Brownian motions. So if you consider two Brownian motions in the plane, so one is called WT, the other one is BT, and you take the inner product of those, so the inner product represents more or less like an angle between those Brownian motions, the probability density can be proved that is exactly the law you've seen before, is x over 2 t squared sinh of pi x over 2t. So that's the relation appears in two different places. So this is about the area of a Brownian triangle. The next thing I would like to study is the perimeter. But you know, when I tried, I noticed that writing those stochastic processes for the perimeter, they are quite difficult because of the square roots involved. So instead of studying the perimeter, I was pleased to study the sum of squares of the sides. So this stochastic process, which is called here Q sub t, and is the sum of the squares of the sides of a Brownian triangle, it's much easier to study rather than the perimeter itself. So the theorem in this case states that the process Qt, which is the sum of the squares of the sides of the Gaussian Brownian triangle, is actually distributed as a gamma function. So the distribution is gamma distributed, and you know gamma distribution is supported between 0 and infinity and depends on two parameters, a and b. So in this particular case, a is equal to 2 and b is equal to 16. So this is the profile of the distribution, is the red curve, which represents the probability law of the sum of squares Qt of a Brownian triangle. And here is the formula of the gamma distribution. So it's a product, it's a coefficient, a product between s and an exponential minus s. Now, the first, we'd like to do more or less the same thing as before. I would like to compute the expectation of the sum of squares, and this can be done, and I computed it to be 12t. So in other words, it's still linear in time. So if t doubles, we expect the sum of the squares also to double. Okay, so everything I talk about so far regards a Brownian triangle, but there are other things we can study in stochastic differential geometry. So the next section I'm going to talk about is about diffusions on manifolds. So when a diffusion diffuses on a manifold, by the way, a diffusion represents a Brownian motion on a manifold, which means on a curved space. So this diffusion is influenced by several things. It's influenced by the dimension of the manifold, by the curvature. So it's influenced by the intrinsic properties of the manifold, but also by the extrinsic properties of the manifold. So if you talk about a diffusion on a surface, the metric, the Riemannian metric, which represents an intrinsic object, actually influences the diffusion, but also the extrinsic, the way the manifold is curved in the space, influences that also. So here we talk about two cases. So case number one, we talk about an extrinsic diffusion. So we have a diffusion which starts from a point on the manifold and diffuses about the manifold. So it's allowed to diffuse also outside the manifold. And the way this diffusion behaves with respect to the manifold can say something about the properties of the manifold. So that's one type of diffusion we can think. So the diffusion lives in the ambient space, and the way it behaves with respect to the manifold can be used to describe the manifold geometry. And the second case, I call it that an intrinsic diffusion, is a diffusion which is not allowed to leave the manifold. So it lives on the manifold, is constrained to be on the manifold. So I'm going to start with the very first case of an extrinsic diffusion to a manifold, and the easiest manifold I can exemplify is just a line in the plane. So we think of a line like this in the two-dimensional plane and a point P situated on that line. So we consider a Brownian motion which starts at P. So when the Brownian motion starts at P, whenever you simulate that Brownian motion, you get a completely different simulation. But because of the symmetry of the picture, the line and the half spaces are quite symmetric, the probability or the chances that the Brownian motion will end after time t on the left half space or on the right half space have to be equal. So in other words, the probabilities are equal to 1/2, to be on one side or to be on the other side. And that's very straightforward. Now things are not straightforward if the line is curved. So if you consider the line to be a curve in the plane, still a plane curve, here we have two regions. So one is the outer region, is the region on the convex part of the curve, and the other one is the inner region on the concave part of the curve. And now if you do the same simulation, you notice that if you consider the tangent line at P here, I know that the probability to be above the tangent line or below the tangent line is 1/2. But because of this extra space here between the tangent line and the curve, it means that the probability for the Brownian motion to diffuse in the outer region will be greater than the probability to diffuse in the inner region, because it's more space outside than inside. So I looked at this property and I tried to compute exactly this probability. Actually, I computed an asymptotics of this probability, the probability to be outside. And this probability depends on the curvature of the curve. So you have a hunch that it must depend on the curvature, but it's not very clear how. So this boxed formula here provides an asymptotics means that these tend to be equal for t small enough. Because when t is large, it doesn't make too much sense. But when t is small enough, it makes more sense. So we have a planar curve, C of S, a point x0 on the curve right here. And we consider, so this is the point where the Brownian motion starts. And the probability that the Brownian motion goes outside is equal to 1/2 plus some extra stuff, and that extra stuff is proportional with the curvature. So the higher the curvature, the more extra stuff you have here, the higher the probability to go outside. And also is proportional with the square root of t, where t represents the time, the time of the, which is the time, the time which is the Brownian motion is indexed over. Now, it's a very interesting property. I wish I can prove something like that for surfaces and show probably it works, replacing the regular curvature by the Gaussian curvature. Probably it works. I didn't prove that yet. Okay, so the second, I talk about two kind of behaviors here. So one is the extrinsic behavior, diffusion, and the other one is the intrinsic diffusion. The intrinsic one means a diffusion which is constrained to live on the manifold S. So how would that look like? So I'm going to consider again very simple types of manifolds, going to more complex type of manifolds. So the very simple manifold which comes to my mind is the unit circle. If you take the unit circle and replace the parameter t, the angle parameter, by a Brownian motion starting at, this is the one-dimensional Brownian motion starting at theta 0, we obtain cosine of the Brownian motion, sine of the Brownian motion. The sum of squares of those two coordinates is equal to 1, and you have a Brownian motion on a unit sphere, or unit circle. Now, if you think, the unit circle is very related to clock. That's why it says clockwise. We measure the angle clockwise or contra-clockwise. So what happens here is that the angle t can be is like time. So if you look on a clock, t represents the time. But if you replace the time by a Brownian motion, it's like you are in a universe where the time goes back and forth in a random way. Of course, our universe is not like that, or at least not from our human perspective. But at some point in time, I had a watch whose hand, I think one of the handler of the watch was going 3 times forth, 3 times back, and I said this must be like a Brownian motion on a circle. Now the Brownian motion on a circle, given by this formula, has or is in its explicit form. But equivalently, it can be also written as a stochastic differential equation or a stochastic system of differential equations. And this is obtained by just applying Ito's lemma to this stochastic process xt. So Ito's lemma is some sort of Taylor's formula or chain rule in the case of stochastic processes. And we obtain a deterministic part here. So these are differential increments. So we have a dt represents the deterministic part and some non-deterministic part given by these infinitesimal increments of the Brownian motion. Now this kind of system, together with an x0 given by this initial condition, has a unique strong solution. And this theorem is a similar theorem to what we have in ODE under the name of Picard-Lindelof. So we have some sort of Picard-Lindelof also here, but instead of Lipschitzianity, here we have that the term here, the drift term, doesn't increase faster than a linear term, which actually happens here. Now, once you have a Brownian motion on a circle, the first question is, let's look at the probability density, and it can be computed in terms of theta 3 functions. Theta functions are functions used in heat transfer along a ring. Now, similarly, we can talk about Brownian motions of a hyperbola, or with a completely different or a similar parametrization and similar system of stochastic differential equations. And in general, we can do on any planar curve. So we consider a planar curve with unit speed. You parameterize, you replace the parameter t by a Brownian motion, and we have a Brownian motion on a curve. And now, like in differential geometry of curves, here we have something similar. We have two processes. So the first process, t sub t, is given by it's some sort of tangent. I call it a tangent process. It's the analog of the tangent or the velocity vector to the curve. And another one is called the normal process, is the analog of the normal to the curve, given by those two. And the increment of the curve, because the curve now, the Brownian motion along the curve is defined by a system of stochastic differential equations, which is given by those two equations. This can be written in a matrix form as written over here, is some component along the tangent process, because dy t is a stochastic process. So this stochastic process can be split orthonormally along the tangent and the normal. So this is like a kinematic decomposition. Now the tangent part and the normal part can be computed explicitly, and the computation is right here. The tangent part represents just increments. Those increments are Gaussian distributed with a mean 0. and the normal part of the kinematic decomposition is given by 1/2 the curvature of that curve evaluated at t, because it's a stochastic process altogether, times dt. So the kinematic decomposition can be written like this, that the increments of a Brownian motion along a curve is given by the tangent part times dt and the normal part times the curvature little dt. Well, everything I said so far is relatively simple because I didn't involve a Riemannian manifold yet. So those are just curves, one-dimensional curves. Actually, the differential geometry for curves is very different than the differential geometry for multi-dimensional manifolds, as we know. So how is a Brownian motion looking on a Riemannian manifold? So if the Riemannian manifold, I assume everybody knows, or if you don't know what a Riemannian manifold, think of a surface in R3 with a metric induced by the metric from R3. And you think of a point x0, which is the origin of this stochastic process, and this stochastic process is defined by an Ito. It's called an Ito process if it can be written like this. The increment, the infinitesimal increment, or the differential dxt, is a function depending on xt times dt, the deterministic part dt, where t is time, plus a diffusion part, another function, sigma, depending on the process, multiplied by the increment of the Brownian motion, dwt. So if you can write like this, you call that an Ito process. So you consider such a Ito process in local coordinates on a manifold, where this b, because the manifold is multidimensional, b represents a vector field. So locally it can be written like this, and the sigma represents a matrix. It's called the diffusion matrix. And this diffusion and this drift term have to satisfy two conditions. So I'm talking about what does it mean to be a diffusion on a manifold. It's an Ito process such that sigma t is the inverse of the Riemannian metric. So you have a Riemannian manifold endowed with a Riemannian metric, and sigma satisfies this. And also the drift vector is related to the intrinsic geometry of the manifold by multiplying or contracting the Christoffel symbols. Now, these are the Christoffel symbols. You can also write this in a completely different way like this, equivalent way like this. And I'm going to make two remarks before I end my talk today, that the diffusion part, the sigma part, depends on G, and G is a tensor. So whenever you change the charts, the tensor doesn't vanish. So that's why when you change the charts, the part sigma cannot be killed. So even if you change the system of reference, the diffusion still diffuses on a manifold. But there are charts in which you can vanish the Christoffel symbols, because Christoffel symbols are not tensors. So you can choose charts such that the Christoffel symbol at a point vanishes, and in other words, the drift term vanishes at that point. So the drift actually depends on the system of reference you choose, while the diffusion not. Now, there is a very famous theorem in stochastic calculus which is called Girsanov theorem. So Girsanov theorem says something very similar to this, but from stochastic point of view, probabilistic or measure point of view. It says if you look at the Ito process in a certain way, which means you change the measure in a certain way, then the drift vanishes. So this is the geometric counterpart of, or the geometric analog of Girsanov theorem of vanishing the drift. Well, I guess I'm gonna stop here. Thank you for your attention. If you have any questions.
Excuse me, you have mentioned the Levy theorem for the area of the Brownian triangle. Have you detected in your analysis also the possibility of having long tail Levy type distribution?
I didn't understand the name of the distribution.
Levy, long tail Levy distributions.
No, I did not. I did not. So I did not look at the Levy's distribution and its tail.
I think one of your assumptions was normal distribution, right?
All the vertices represent Brownian motions in the plane, and they are normally Gaussian distributed, two-dimensional Gaussian distributed.
Excellent. Yeah, just as I remember from Romania that very much liked your talk because of the closed form solutions. One remark is that Dr. Robert Brown actually studied Brownian motion or discovered it in pollen grains on water. So there is a direct connection here with botany for sure. Are there other questions? No? Then I would like to thank you again, OVIDIU, for your excellent talk, and yeah, and I wish you a lot of success with applying Levy distributions or something. Let's see where this goes. Huh? Okay, thank you very much. So the next speaker is Shaheen Hilare. Shaheen is a mathematician from Iran, and he's currently living in France. And he has a small company with his wife, Raime, and they've been working on a lot of